All right, so here's what we worked on today in class. Just want to go over this. First of all, we are looking at trying to identify key features of quadratic functions. In this particular example, I can easily see two things. X-intercepts. The form of this equation that we're in, where it's got everything in factored form, shows me x plus 4. I can basically set it equal to 0. And if I set these two things equal to 0, I find out that the x-intercepts, maybe I should just get rid of one of those. Not that much. The x-intercepts here are -4 and +6. Okay? Now, if I take that information to a graph, besides the fact that x times x is x squared, which is a positive term, right? X squared has a positive 1 in front of it. That's telling me it opens up. This number in front, which we commonly refer to as the a value, tells me that the graph is, whether it's positive or negative, tells me whether it opens up or down. So as you can see in my picture, I put a dot on -4, a dot on 6. And basically, I was just trying to say, hey, when I look at this form of the equation, I know some basic things like where it crosses the x-axis, and I know that the parabola opens upwards. Okay. I know I got a lot of other stuff on screen, so let me explain that. They're asking me to put this in something called standard form. Now, standard form really means this right here, decreasing order of exponents. So I had to multiply them together, which in this case means I have to do FOIL because you're multiplying two binomial terms together. Now, I don't care how you do FOIL. You can kind of see how I drew the arrows like you've seen before, like in an Algebra 1 class before. Firsts, outsides, insides, lasts. That's what FOIL stands for. It's just a way to do it. There's other ways to do it. Like I showed two examples here. Some people like to use the box method where you put one on the side and one on the top, and you literally match things up, multiply them together, and add any like terms. Here's another version of the same thing where you stack one on top of the other one and then do it kind of like you did two-digit multiplication back in elementary school and maybe middle school kind of thing. But no matter which way you like to do it, you should come up with x squared, -2x, and -24. Whichever way you like to do it, that's what you should come up with. Now, the thing that has the degree 2 polynomial term, that's called our quadratic term. Our linear term has degree 1, and our constant term has degree 0. Now, what do you mean by degree 0? I literally mean next to that -24 is an x to the 0. Now, nobody writes it because everybody knows that anything to the 0 power is 1. So why would anybody write x to the 0? Nobody does. But it's true that it's there. So they did two things. They asked me for the standard form, so I did that. I did my FOIL. And then they asked me to identify the three separate parts, quadratic, linear, constant. Okay, so I went to the next one. The next one was given to me in something called Vertex form, which we will talk more and more about. And I want to show you a couple things that I forgot to talk about. We can easily see that the graph moved left 3 and it moved down 7. Okay? Remember that changes on the inside go against your common sense, changes on the outside match your common sense. And what does that 2 on the outside do? Well, that would be what we call a vertical stretch by 2. Because it's on the outside of the function, it affects the y value, and changes to the y match our common sense. Now, what does it mean when you square something? It means that you multiply it times itself. So you see that I wrote it out twice. And I would suggest you would start with the foiling part. That's really where I would suggest you start. X plus 3 times x plus 3. And when you do that, and if you see the box that I did over here on the side, I did x plus 3 times x plus 3, and you can see that's the x squared plus 6x plus 9. Well, what do you do next? Then you do your distributing, right? Distribute, distribute, distribute. And that gets me at the bottom here, 2x squared, 12x, 18. And then, of course, you still got your minus 7. The 2 on the end are constant terms. They can be added. They're like terms, and they can be added together, which is why my final equation ended up looking like this. And when we ask you to identify the 3 pieces, we've got the quadratic at the top. We got the linear being the one with the, so we got the squared exponent goes for the quadratic. The linear is the degree 1. And then the constant, the one without a variable, is the last one. Quadratic, linear, constant. Okay. So if you want me to give you more generic looking forms of these features or these different forms of the equation, this would be called standard form. Okay? Decreasing order of exponents, and they use the coefficients a, b, and c. Vertex form looks a little bit different, and it's more like the second one that you started with. It looks like this one. That's because the vertex of a parabola is at the coordinate. The vertex of a parabola is at the coordinate h comma k. H comma k. So when you look inside here, you should be easily able to tell what the h and the k are. So for the last example up there, letter B, I knew that the vertex was -3, -7. -3, -7. That's why we always say it's backwards of your common sense on the inside. It's exactly like what you think on the outside. I'm kind of wondering what they want for the standard form that right here it says parabola. That is the name of the shape, okay? So as we draw these things, as I draw what's called a parabola, it's going to look like kind of like a U shape. It's got a curve to it. It's not like an absolute value, which looks like a V, but it has more of a curve. Now, can it open up or open down? Yes, it can open down too. That's true. Now, the axis of symmetry is a line that cuts it in half. In our case, we're going to have vertical lines that cut it in half. And vertical lines are always x equals a number, right? These are vertical lines. Now, I can get really specific. I can go one step further, and I can tell you how a shortcut for finding that. And it has to do with using the a and the b value. It says that and a lot of times they will abbreviate this AOS for axis of symmetry. but the axis of symmetry is found by using this little shortcut. X equals the opposite of b over 2a. That's a b, not a 6. And we do need the opposite, and that's why I put that negative in front of the b. The opposite of b. Now, I do want you to notice that this a here and this a here are exactly the same. Now, I know in the vertex form, you don't see b and c. They're kind of hidden in there. We'll talk more about that later. But the A is very obvious that it is the same in both. Let's go to the next slide. For the graph pictured at the right, identify the vertex. Okay, well, it looks like it's right about there. That would be 1, 2. Axis of symmetry, line right down the middle. That would be x equals positive 1. Oh my goodness, look at that. It matches the x value of the vertex. Interesting. What's the domain? Well, if you squished all these points onto the x-axis, we did that kind of thing before. Maybe I should try that with this one. Whoops. Here's the same picture of the equation that we're sitting there, and we want the domain. Now remember, I gave you the idea of taking your two fingers, putting them on the y-axis, it changes to light blue, and smashing the graph down onto the x-axis to tell domain. And I asked how much of the x-axis got covered. And you would probably come over here and say, oh, Mr. Stailey, it went from negative infinity to positive infinity. It covered the entire x-axis. That is true. But then when you come back and take a look at it, and now we're going to do the same thing but smash it onto the y-axis by grabbing the x's and smushing it together toward the y-axis, you can see that it starts out at 2 and then goes up from there. So it starts out at 2 and goes to positive infinity. You can see that in the picture. Starts at 2 and goes up. I do want you to give me interval notation on this stuff, okay? Okay, graph this parent function, y equals x squared. I mean, can we do this with technology? Well, of course we can do it with technology. That's pretty easy, But you also need to be able to do that by plugging in points, right? And squaring them and seeing what happens. Looking at there being a matching pair on either side of the middle. Yeah, there are y values that are matching pair. And you can take a look at the graph, and you can, here, I'll zoom in to make sure I get a good graph. 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. Well, there's my picture. Not my greatest parabolic drawing. Whew, man, sketchy. What's the domain of that? Well, if we did the same thing and smashed it onto the x-axis, we would find negative infinity to infinity. If we smashed that onto the y-axis, we would start not at 2, but this time at 0 and go up, up, up from there. What's the vertex? Well, that point at the bottom where it changes directions is 0, 0, and the axis of symmetry, x equals 0, right down the middle. X equals 0, right down the middle. Quadratic graphing pattern. Ooh, okay. All right. Let's see here. When the a value is 1, over 1, up 1. Over 1 again, up 3. over 1 again, up 5. This is called the 1A, 3A, 5A method of graphing. And it's a useful thing. If you know the A value, you can triple it to find the next point. You can multiply the original A value by 5 and find. So as you're looking at this is not like slope. Slope, for a line is a constant change, but this isn't a slope. This is changing, because you're going up by 1, and then you're going up by 3, and then you're going up by 5. Hey, if that A value becomes a 2, then it's going to go 2, 6, 10. We're going to practice that in class, okay? And if it's negative, what happens? Oh, well, now it's going to go down, not up. So, yeah, if you come over here on this graph, you can kind of look at it. So the whole strategy on the blue one, over 1, up 1, over 1, up 3, over 1, up 5. What did I miscount? Over 1, up 1, over 1, up 3, over 1, up 1, 2, 3, 4, 5. Yeah, okay, yeah, I miscounted. Okay. And then, of course, you got duplicate points on the other side. Well, what if that changes? What if the A value is a 2? Then it's over 1, up 2, over 1, up 6, 3, 6. It's harder to show just because I'm kind of... So maybe I should do this. Yeah. So starts out at 0, 0. And then goes over 1, up 2, over 1 again, but this time up 6. 6 plus 2 would be 8. Over 1 again, this time up 10, which would be 18. So you can see those dots follow the green one. So on my green parabola, it's still following this 1A, 3A, 5A pattern, but if the A value is 2, then 3A would be 6, and 5A would be 10. So it's changing by faster amounts, which means it goes up quicker. But that 1A, 3A, 5A is kind of a nice way to graph things. And I think that's what they were getting at down here. Now, if the B value, I notice right here, there's no B value. That means that the B value is 0. So, no left or right movement. So the vertex doesn't shift at all, left or right. That does happen sometimes. You will see things that, but I just wanted to point that out to you, that if we don't see a B value, that means we know that the B is a 0. Okay, let's go to the next. Okay, so in this case, the A value is a 1. We can see that right in front of the squared term. So the pattern for that, for 1A, 3A, 5A, would obviously be just plain 1, 3, and 5. Now, the vertex. Well, if we do that whole opposite of B over 2A trick that we talked about, the B value is 0, and on the bottom we have 2 times 1. Well, what is the opposite of 0? Isn't it still 0? And then on the bottom you got a 2, so 0 divided by 2, still 0. So we all know that the x value is 0. How do we find the y value that goes with it? Literally, we're going to take this y value, or this x value, and come up here and plug it in, right? Because this is an x value. And when we plug it in, we have 0 squared minus 4. We now know that the vertex is at 0, -4. Well, that makes sense because you do not see a left and right shift, so the graph doesn't go left and right, but you do see a down 4 shift on the outside. Okay? And if we use the pattern to 1, 3, 5, we go 1 to the right, 1 up. 1 to the right, 3 up. 1 to the right, 5 up. And then we're just going to copy points to the other side. Whoops. So we can draw our parabola. Okay? So now my a value is negative. So if I'm using the 1a, 3a, 5a method for graphing, this would be -1, -3, -5. So this means it's going to be opening down. Now, as you can tell, no shift left and right, but we do have an up 5. Now, we could use our pattern, our opposite of b over 2a, and that would be the opposite of 0 over 2 times -1, or 0 over -2. We still know that is 0. Whoops. If we plug that into the equation, we will get a 5, which matches our what we know. We know there's no left and right, but we do know it goes up 5. And now we can use our pattern, our -1, -3, -5. So over 1, down 1. Over 1, down 3. Over 1, down 5. And then you just want to duplicate it to the other side. And draw your shape. That's what it looks like. So, ignore the negative. What does that mean, ignore the negative? Why? If a is greater than 1, vertical. Oh, I see. Why they're saying ignore the negative. So, the negative causes the graph to flip upside down. But that has nothing to do with what we call the stretch or shrink. If a is bigger than 1, we call it a vertical stretch. If a is a fraction, right? Fraction. Then we call it a vertical shrink. Because we're making the y values smaller. When we make the y values smaller, it becomes a vertical shrink. Okay, so let's see here. I know that the a value is 3. If I use the 1a, 3a, 5a, that's going to be 3, 9, and 15. Now, sometimes you can't get everything on the graph. Maybe you get the 1a and the 3a, but not the 5a. Okay. Now, what are we starting at vertex-wise? Well, it doesn't look like you shifted it left and right, and it doesn't look like you shifted it up or down, so guess what? 0, 0. I can go through the whole opposite of b over 2a thing, but you can clearly see nothing has happened to that, except a vertical stretch. So, start out at the origin, over 1, up 3. over 1 up 9. Okay, there's no way I'm getting 15 after that. So I better duplicate it on the other side. There should be a matching point. Now, if you say to me, matching side or opposite side of what? Remember, it's that axis of symmetry. It's the line that goes down the middle. Sometimes you can easily see it, or maybe you need to draw it in so it helps you. You know, kind of visualize what's an equal distance on both sides of that line. Graphing the next one, I got a -2. If I use my pattern, that's going to be -2, -6, -10, 1a, 3a, 5a. We did not go left and right at all. But we did go up 7. So, what does that say? 2, 4, 6, 8. Oh, okay. So we did go up 7. So that's right there. All right. Over 1, down 2. Over 1, down 6. It's going to land me right there. Over 1, down 10. That's going to take me way off the graph. All right. So you can put in your axis of symmetry if that helps you to get your points on the other side. But there's your picture. All right. 1/2. Now, if I use the 1a, 3a, 5a method on this one with 1/2, so that's going to be 1/2, 3 over 2, and 5 over 2, which translates to 0.5, 1.5, 2.5, if you're a decimal fan. It's probably going to be easier on the graph if you do it that way too. Now, it has not been shifted left or right, but it has been shifted down 4. So we know that we're starting at 0, -4. Wait a second. Yeah, okay. Yeah, we're good. All right, now we're using 0.5. So over 1 up 0.5. Over 1 up 1.5. Over 1 up 2.5. Is that right? Yep. And then, if you need your axis of symmetry, draw it in. Plot your dots going the opposite way. Draw in your curve. So it definitely was nicer to use the decimals on that one. Okay, I think that's it for these notes. Let me check. Yep, that was it. See you later.